Okay, so where we were last time, we talked about the product topology and the box topology. So these are two different topologies you can put on the Cartesian product. And so for the infinite Cartesian product, we usually prefer the product topology. And one of the reasons can be seen in the following theorem, which says that a function to a Cartesian product is continuous if and only if each of the coordinate functions is continuous. And that seems like a very straightforward thing to be able to demand. And it's only true for the product topology. It's not true for the box topology. So we didn't do the proof of this, right? Right. Okay. The proof is very similar to what we did before. So the one that is true, let's show F continuous implies coordinate. Continuous. And this implication is in fact true for the box topology. And the reason for that is, well, you just look at the projection functions. Right, so the projection function from product to, oh, hang on, let's call it beta to x beta is obviously a continuous function. In any topology, right? Because if you've got an open set here, it gets pulled back to something which is x alphas everywhere except in the beta coordinate, and it's your open set u beta that you pull back there. Okay, so that's continuous in both the box and the product topology, and of course the coordinate function then is just the composition of the function with the projection, and so therefore it's continuous. So if f is continuous, f alpha is continuous. Composition of continuous. Okay, so that one's easy, and it works for everything. So why, before we show the other one, let me show you why it fails for the box topology. Okay, so consider the function that takes, so let's take the function f that goes from the reals to this countably infinite vector space. Actually, the easiest way to think of this is just as the space of sequences. Just like you've got x1, x2, x3, x given by f of t equals t, t, t forever. And that is, if we think that can't be continuous, only. I mean, we know that a constant map is going to be continuous because all continuouses, but this is kind of like the simplest non-constant map. Okay, now what we've got to do is show that the inverse image of an open set is not image. So let's look at this little open set, which is -1, oops, -1, 1, cross -1/2, 1/2, cross -1/3, 1/3, cross, and in the nth position, it's minus an n, 1 on n, etc. Okay, so this is an open set in the box topology because at each coordinate we've just got an interval. And already you might be seeing something making you uneasy because sure, every component is open, but somehow in the limit, it's going to a point, that's what's going to screw us up. So, because let's have a look at an F inverse of B. So we want F inverse of B to be an open set in R. Well, I think it's just going to be the singleton zero, because what happens if it was an open set? Then it would contain, if open, it would contain some -1 on n to 1 on n, right? It contains some open interval, but for when we go past that nth thing here, when we pull its image back, it's going to be less than that. So yeah, basically the inverse image is just going to be the point 0. So that's why it fails to be continuous. It's just something to do with infinity, just like which we've got to worry about. Okay, but as I said, yeah, so that's why it fails this one. But why don't we get into that trouble for the product topology? What did I write for that? Okay, so we've got all the F alphas being continuous. So what we've got to do then is just show that F inverse of some sub-basis element of the product is open. So, because remember, F is going from A to some there. But in the product topology, a sub-basis element is something of the form I inverse and the reason for this, of course, is because we can sort of generate any basis element from that. Right. So let's have a look at this then. What can we do with this? Well, we can write that as pi b b. But this is just exactly F beta. Because I mean, this is what the definition of the coordinate function is. And so, but now we're given that this is open, this is continuous, so this is open. And so that goes ahead and does it for us. Okay, so as I said, this is why we kind of prefer the product topology. Let's have a look at metric topology now. So the nice thing about metric spaces is that they have a metric, and this gives us a concept of distance, and this turns out to be really powerful, and it, as we'll see. So a metric has the following properties. It's going to be positive, and it's only equal if at the same point, so the distance from x to x is 0. It's symmetric, and it satisfies the triangle inequality. So you've seen this before, right? Okay. And the nice thing it gives us is these balls. So given any epsilon greater than 0, then we can look at, we have a ball centered at x, is all those points whose distance from x is less than epsilon. And sometimes we'll have the D here, and sometimes we don't, depending upon. Okay, now it's a fact that once you've got a metric on a set, you have these epsilon-centered balls, and they turn out to be the perfect candidate for open sets. Okay, and so if you have a set X and a metric D, you take the collection of all such of all balls for every X in our space and every epsilon greater than 0, and we can use that as a basis for the topology, and that's the metric topology induced by D. And it's a fact that you've got this metric that lots of nice things then, powerful results then result. So the first thing we're going to show is that it actually is a basis, and that's actually pretty straightforward. So before I go, one of the nice things though about when you've got this distance function, basically then you get analysis. You get all the things that we don't know, you know, all those epsilon delta arguments, etc., that you've seen before. So this shows you that at the heart of analysis is topology. So that's an important thing to realize. So why is this a basis? Okay, so remember, what are the two conditions of a basis? Every element has to belong to a basis element. Trivial, right? Because a set of balls set it at any arbitrary x. So x is in its own ball. So that's the second thing is what? That if you have two basis elements, then there exists a third basis element which lies in the intersection of the two. Okay, and we can just have that as a lemma here. y, this lemma will help us with that. So if y is any point in a ball, then there exists a basis element lying within that ball. And so the whole thing is then, well, you've got to find delta. And of course, delta is just going to be epsilon minus the distance between x and y. Okay? And so since this is less than epsilon, this is going to be greater than 0. And so that is in fact the basis element. So the proof of that is basically following from the diagram, because if Z is in this ball Y delta, we've got to prove that Z is also in this ball. Okay, and this is where you have to use this. So the distance between Y and Z is going to be less than delta, but delta is epsilon minus the distance between x and y. And the distance between x and z, which we want to show is to be less than epsilon for it to be there. What do we use? Well, not this lemma. I mean, we've used this lemma to find a candidate, but now we've got to use some property of the metric. So we've got to put this in terms of the distance between x and y and z.
Yeah,
right, we use a triangle inequality. But that's less than the distance from x to y plus epsilon minus the distance from x to y. They cancel, and so it's in the ball. Great. So the diagram doesn't mislead us. The diagram is actually what is happening. So, and so then as a corollary from that, we get our, from that then the second thing holds true, because what are we going to do? The second condition is what? We've got two basis elements. They intersect, and let y be here. Then why can we put a ball around here? Well, since y is in B1, there's a ball such that it's contained within B1, and there's a ball y delta 2 such that it's contained in B2. So what are we going to take as our delta? Right. So if we let delta equal the minimum of delta 1 and delta 2, then that is going to be true. Okay. And so as a corollary of that, we have a really, really useful criterion that we can use to determine whether a set is open or not. And this is kind of like the standard way that you show anything is open. A set is open if and only if for every element of the open set there's a delta greater than 0, such that the ball centered at y with greatest delta is contained in the open set. That is super useful. Examples. Given any set, we can define the discrete metric, which is that the distance between any 2 points is 1 if the points are different, and it's 0 otherwise. Okay, this is a metric, right? Because it satisfies the first criterion. It's symmetric, and it satisfies the triangle inequality because the distance from x to z is 1, and that's less than the distance from x to y, which is going to be 2, unless, of course, you've got any points which are doubled up, in which case it's going to be 1 if z equals x or y. Okay, and the topology it gives, of course, is the discrete topology. And why is that? Well, if you look at the ball centered at x with epsilon 1, that's just going to be the singleton x. And so that means the singleton x is an open set, and any topology where all the singletons are open gives us the discrete topology. The standard metric on R given by absolute value of x minus 1 is also a metric, right? Because it's going to be positive unless x equals y, in which case it's going to be 0. Because the absolute value is going to be symmetric, and it satisfies the triangle inequality because of the triangle, because of the real triangle inequality. Okay. And the topology that it gives is the same as the order topology. And why is that? Well, that's because the balls are open intervals. So it's the same basis in both topologies. And so for the rest of class, we're going to show that Rn and R omega are also our metric topologies. So an important side note, if you've got a topological space, then we say it's metrizable if there exists a metric Z on the set X, which induces the topology on X. And a metric space is a metrizable X together with a specific metric that gives the topology. Okay. As I said, this is going to be important. So it's nice if you have a topology. It turns out that if you can show that there's a metric underlying it, then you've got a whole host of theorems and stuff and machinery that's at your help. We've already started sort of classifying topologies, like we've seen T1, we've seen Hausdorff. Metric is better than Hausdorff. So, you know, there's these succeeding sort of categories of topologies, one more powerful than the other, which you can then do. The main thing is, of course, that if you've got a metric space, then you can do analysis on it, which is a whole bunch.
Are we saying a metric space has to be Hausdorff?
Hmm?
Are we saying a metric space is Hausdorff?
Isn't that obvious? Because what's Hausdorff? Remember, a space is Hausdorff if you can put open sets around them, disjoint open sets around them.
Right.
So if we've got points x and y, right, and if x doesn't equal y, then there's a distance between them. And so you just look at the ball, half of radius, half the distance from between x and y, and that's two disjoint things. So metric, because you've got a distance, Hausdorff comes free. Of course, you know, the only way for it to be metrizable might be to put the discrete topology on it. And that's not really going to do you any good because then everything is true basically in the discrete topology. So, but it's usually a space with the topology that you want. You want to show that that is metrizable. And in fact, what we're going to do in the second half of the course is prove various metrizable theorems so that the space is metrizable. So a list of conditions on a space that you can then prove that there has to be a metric that's underlying it. Okay, so because we're doing metric space, we've got topology and we've got analysis. So metrization, right, is a topological question. But typically what happens is that the properties of a certain metric are like analytic problems and they're not topological problems. So for example, a really important analytic property is boundedness, whether a set is bounded or not. And just to remind you what that means that a subset is bounded if there is a number m such that for any 2 points in our subset, the distance is less than m. Okay? And in fact, you can talk, if you've got a bounded set, you can talk about its diameter as being, you know, the maximal distance between any 2 points. Boundedness is an analytic property. It's not a topological property. So remember what a topological property is. Topological property is such that if you've got a space, that all spaces homeomorphic to that space should have that property. And we know straight away, for example, that the open interval 0, 1 is homeomorphic to R. So boundedness is something that can't possibly be topological. But it's a really important thing in analysis. So straight away you can see that there's going to be distinction between topological things and analytic things. In fact, showing you like this, sort of emphasizing this point here, let's have a look at this theorem here. So say we've got a metric space with D, and if we define a new metric to be such that the distance between x and y is the minimum of either the distance between x and y and the old metric and 1. So that means the maximal distance between any 2 things in the set is going to be 1. Then this is a metric. And why is it a metric? Well, what do we got? This is going to be always going to be positive, right? Because 1 is always positive, this distance is always positive. Distance between x and x, or the distance here is 0, so that's going to be the distance between it. So is that it's symmetric. And so the only thing you really have to show is the triangle inequality. So let's show the triangle inequality. So if we're comparing the distance between x and y and the distance between x and z and distance between y. Okay, if any of these is 1, then we're done. All right, because this at most can be 1, So if one of these is 1, then we win. Okay, so what happens in the case if these two guys have distance less than 1? Then when we compare these guys here, if these distances are both less than 1, then this is equal to the distance between x, z, and by the definition. And so we have that this is going to be greater than or equal to the distance between x and y. But by definition, this is always going to be greater than or equal to the distance between x and y, because this is either going to be this, or if this is too big, this is 1. So the triangle inequality follows. Okay, now why? So it is a metric. Why does it give the same topology? Well, let's come up with a basis that's the same. So let's consider the set of balls such centered at x, radius epsilon such that epsilon is less than 1. Okay, so this, so let's call that, and oh no, not dash it back. Okay, so we've got, so consider these two collections. By definition, they're the same collection, right? Because we just reciprocate. But both of them are bases for the topology, because any set, any ball which is bigger than 1, you can write it as a union of epsilon, gamma, where gamma is greater than 1, is going to be the union of the balls where y is in that, let's call that set C, y epsilon, where epsilon is less than 1. So you can write any bigger ball as a union of smaller balls, kind of trivially. Well, you've got to be careful with epsilon because you don't want to go past it. So epsilon is either 1 or the distance between y and the boundary, something like that, if we want to be kind of precise.
So if we use a number other than 1, like when we define v bar, so if we use the number greater than 1, I think we'd still get a metric.
Yes.
And it would still induce the same topology.
Yeah.
If we use the number less than 1,
No.
I don't think we'd still get a metric, would we?
Yes, we'd still.
How would the triangle equality
This would still be true, right? Say it was a half, right? Again, if these numbers were bigger than a half, were half or hang on, the original numbers. If these numbers are bigger than a half, then this would be true. Okay, so we've got to assume then that these distances are going to be less than a half. Okay, in which case those distances is going to actually be these distances, the real distances, and we get the same comparison. So it's actually true for any number. So all you're going to do is fix a number, and then that creates the biggest bound, and it's going to be the same topology because the balls of those, as long as it's a fixed maximum, you can then, as long as it's positive, you can then generate any other open set. And of course, the thing that, so we call this the standard bounded metric. We just use one just to be, that's what's standard about it. And of course, the thing is that every subset of X is bounded. So any topology can be given, so any metric topology can be given a metric such that every set is bounded. So this just crushes the idea that boundedness is any way connected with topology. Things that are connected to topology are things like connectedness, whether the set is connected or not, or compactness. But these are things that we're going to sort of study next. So they're topological questions. Norm. So this is I don't know if you ever watched Cheers. Okay, this is a joke about Cheers. There's this character in this show called Norm, and whenever he comes into the bar, everyone yells out, Norm. My wife runs that way. Anyway, so you say you've seen norms before. Okay, so the idea of a norm is it's kind of better than a distance. So you need a linear space for that, you need a vector space for that, and so that means you've got a zero. And so when you talk about a norm, you don't need two elements now. You just talk about the norm of a single element, and that's the distance from the origin for that. And so so norms sort of satisfy everything a distance does. So the norm of an element is positive unless the element is zero, in which case the norm is zero. You've got a triangle inequality. So the norm of x plus y is less than or equal to the norm of x plus the norm of y. Oh, and you've got a scalar property. So the norm of a scalar times x is equal to the absolute value of the scalar times the norm of x. And so anytime you've got a norm, that gives you a distance function by just looking at the norm of the difference between the two elements. So famous norms is the Euclidean norm, which is like the idea of Euclidean distance. So in the Euclidean norm is just the normal distance, the Pythagorean definition of distance. I was brought up to think of this as the two norm, but it's not in the book. I call it the Euclidean norm. Another norm is the square metric, where I think of this as the infinity norm, so the supremum norm, where the difference between x and y, the distance between x and y is a maximum of the differences in the coordinate functions. And actually, you can, for any number between 1 and infinity including infinity, you can come up with a norm. So where by infinity I mean this, and the p norm is equal to the summation of xi minus yi to the p, and we take the pth root of that sum. Okay. And so that gives you a perfectly good norm. And so for example, in Euclidean space, the 2 norm gives as the ball around the origin looking like a circle like that. Whereas the square norm, the ball looks like a square. Which is why they call it square norm. And the one norm gives you a square like this. Right, because this is 1 to infinity. The one norm is just where the sum of the absolute value of the differences of the coordinates. And then any p between 1 and 2 is kind of like a little, will look like in here, and any p between 2 and infinity would look kind of like that. So for example, 3 over 2 would look like that, and 3 would look like that. So they're interesting from an analysis point of view, all these p norms, but from a topological viewpoint, they're not interesting at all because they all give the same topology. So for example, on R1 on the real line, these metrics just coincide with the standard metric. Because if there's only one coordinate function, then you know the square root of something squared is just going to be the absolute value. So, and if there's only one thing, there's only one thing to take the max over. So they're all the same thing. And so that just gives you the standard metric. On R2, then they give you different balls, but as we've seen, these basis elements the basis elements are circles and squares, and we've seen that generates the same topology. And that's the standard topology in R2. And if we've got time, we're going to show that these two metrics induce the standard topology on Rn. And actually, that's going to be true for any of the p norms as well. So it's exciting to see them, but from a topological point of view, they're not going to really provide you with any interesting examples. But of course, in analysis, they will. I guess one last point is, why are these norms? And that's something you prove in analysis. The only thing of interest, of course, is to prove the triangle inequality. All the other ones are trivial. This is actually pretty trivial because the triangle inequality from here actually follows basically straight away from the triangle inequality here because it's defined to be the maximum, then let's say x and y attain its maximum at the ith coordinate. You just look at the ith coordinate and it satisfies the triangle inequality there. And you might say, well, maybe in the sum, those things will occur in the jth coordinate, but that doesn't matter because that'll only make the sum bigger. So the fact that this is it gives you a norm is trivial. This you need Cauchy-Schwarz. Have you done the Cauchy-Schwarz inequality? Okay, it kind of follows from that. And for the p norm, you need the Holder. Have you seen the Holder inequality? That's just a generalization of Cauchy-Schwarz. So So it's like with P. What's Cauchy-Schwarz again? It's that, so write down what it is. Summation of x, k, y, k, yeah, is less than square root of summation of x squared times the summation of y squared. That's what you remember? To hold the inequality, you replace that by P, and this by Q, such that 1 plus P plus 1 plus Q equals 1. And that's the Holder inequality. And so this, the proof is similar. But since we're not doing analysis, we'll leave that alone. Okay. Okay, so we want to show that the topology given by the Euclidean norm is the same as the topology given by the square norm. And for that, we'll just need this little lemma here. It's a useful little lemma, and it tells us how to compare two topologies given by how to compare two metric topologies on the same set. So say we have two metrics on a set, and we have the topologies they induce. Then when is one topology finer than another? Well, that's going to be the case if for every x in our set and for every epsilon greater than 0, there exists a delta greater than 0, such that there is an open set in the finer topology, which is contained within the coarser topology. And this is really the same as lemma 13 point something, 13.2, I think it was it? 13.3. And so this is basically rewriting 13.3 for metric topologies. So if this is finer than T, then given this ball here in the metric D, then since this is finer than that, then we can invoke lemma 13.3, which says each x and basis element of basis element B in curly B. So let curly B be a basis for T, and let curly B prime be a basis for T prime. There is a basis element B prime contained within curly B prime such that X is contained within B prime is contained within B. But this is exactly what this says, right? Because basis elements here look like this, and basis elements here look like this. So this is just rewriting, and then conversely, if we've got B, D prime, X delta contained within B, D, X, epsilon, if that's true for all epsilon and X, that means we, given any basis element here, we can find given any basis element in T, then there's going to be one of these balls that's going to be contained within it. Of course, because of base, you never know what basis element you're going to be given, but within that basis element, there has to contain a basis element like this. But then by the hypothesis, we can find a delta such that this is true. And so going back through 13.3, we then conclude that T prime is finer than T. Okay, so this lemma then gives us a way of comparing metric topologies. And we're done. Okay. So we'll finish off the comparison next time. We're going to show that it's going to be the same. And not only are they the same, but they're the same as the product topology.
So with the whole being able to use any number for a bounded metric thing, it's kind of like saying you always have more epsilon balls than you do in your basis.
Yeah.
That's kind of interesting.
Yeah. But I mean, also, like the open interval 0, 1 is isomorphic to homeomorphic to R, but so is the open interval 0, 2. So you can use, or the open interval 0 or half. So you can use any number for the bound. Whew. Okay, let's stop recording.